Hi, everybody. Welcome back. Um, so in the first part of the talk, I kind of gave an overview of what the gap distribution question is, and in particular, a theorem for double slit tori in the gap distribution gap distribution double slit tori. But I said next to nothing about the proof. So in the second part of the talk, I want to give an indication of one key element of the proof, and I also want to tour kind of the history of gap distributions and translation surfaces. So kind of the way I'll break it up, I guess, is at first I'm going to look at kind of lattice surfaces, and then I'll look at non-lattice surface and kind of the results in these situations. So I won't define explicitly what a lattice surface is, but we should kind of think about it as a highly symmetric translation surface, an example of which is the regular octagon. And then an example of a non-lattice surface is, for example, a generic double slit torus. Okay? So kind of the first, maybe explicit gap distribution for a translation surface was given by Athrea Chung in 2014, where they considered the case situation for the torus. And what's really interesting about their result is they're somehow recovering a result from the 70s by R. Hall, where he considered gaps of Ferri fractions. And so what Horocycle's work kind of does is they recover this result by geometrically reinterpreting it as a result for gaps of slopes of the torus. And they were able to prove kind of this result using dynamical methods, whereas Hall's original techniques were kind of analytic number theoretic techniques. So shortly after the torus was considered, Horocycle and Lelièvre considered the situation of gaps for the golden L, as pictured here, where phi here is a golden ratio. After that, ionic work looked at the regular octagon, that was pictured in the previous slide. And then more recently, Taha looked at the gluings of two regular 2n+1 gons. So Taha's results aren't exactly stated in the language of translation surfaces, but they can be reinterpreted as such. Okay? And so now what are some of the, so what are the kind of defining characteristics of these results? The defining characteristics of these results are there's no small gaps, and this is actually consistent with a result of Horocycle that says in the lattice case we better not have small gaps. Their kind of parameter space that they were working on was somehow two-dimensional, and in all of these situations there's completely explicit gap distributions. Okay, and so now if we were kind of to turn to the non-lattice surface, maybe the first result in this direction was given by Horocycle, where they looked at a generic translation surface with respect to Maser-Beach. And they showed that the gap distribution exists for almost every translation surface, it's actually the same. But because of the situation they're working in, they're looking at a generic translation surface. They're not able to get any explicit results. And in spite of that, though, they are able to say something about small gaps. Right? They're able to say that small gaps actually characterize non-lattice surfaces. So this was maybe the first kind of result on gap distributions for translation surfaces. After that, work came out with a result for genus 2 translation surfaces with a single cone point. And her situation was kind of a 6-dimensional parameter space. And because of the high dimensionality of the parameter space, her results are very non-explicit. And then more recently, kind of where my work kind of fits into this series of papers is for double slit tori, right? These are genus 2 translation surfaces now with 2 cone points. And in my situation, the parameter space is 4-dimensional somehow. And it's the first gap distribution for it's the first explicit gap distribution for a non-lattice surface, right? And here's a picture of a double slit torus. Okay. And so this has kind of been the history of it. And I should mention kind of the results by work and by me, and in the kind of lattice surface case are kind of trying to understand this exceptional set of translation surfaces, right? Horocycle said a good amount about a generic translation surface, but it's kind of, very common in ergodic theory. Okay, once we have some ideas of the generic set, we want to try to investigate properties of the exceptional set and kind of what's the same and what's different. So yeah, so that's kind of a small tour of the history of translation surfaces. And now in the next piece, I kind of want to walk us through one key element of how we prove a slope gap distribution question. And the guiding philosophy is the following. Okay, so questions about a fixed translation surface can often be understood by considering the dynamics on the space of all translation surfaces. And right, there's kind of this philosophy in translation surfaces and homogeneous dynamics that kind of amounts to this. Some famous examples of this, of course, are Mazur's criterion for unique ergodicity. Another one is kind of Veitch's theorem, Veitch's dichotomy about directional flow on a lattice surface. And so I'm really happy that I kind of get the chance to kind of walk us through another instance of this really powerful philosophy. And I should mention, so right, what are we going to be walking through? We're going to be looking at kind of the gap distribution of a double slit torus and trying to turn this into a dynamical question on the space of all double slit tori. And I should mention kind of this instance of this philosophy, of this guiding philosophy here, was not done by me. This was done by several authors, like Athreya, Shaika, Chong, and Lily Avra, for example. So, but I'm really happy that I can kind of present their kind of instance of this guiding philosophy. Okay. So now let's formalize a little bit. The kind of translation surfaces that I want to consider are double slit tori, right? So I want to let E denote the set of all double slit tori. You know, on the left here is one example of a double slit torus. On the right is another example of a double slit torus. And I want to just kind of look at all of them. And I want to realize, you know, that there's a natural SL2R action, right? I keep kind of saying, you know, a dynamical question in the space of all double slit tori, but there's no dynamics, right? This is just a space. And so I want to kind of consider the linear action of SL2R on E. And what do I mean by this? I mean, well, what's an element of E? It's just a polygon in the plane. And so SL2R knows how to act on polygons. Right, so for example, if I have a double slit torus here and I want to act on it by the matrix 1, 1, 0, 1, this matrix knows how to act on something in the plane. And so what I want to do is I want to act on this whole picture, and I'll produce a brand new translation surface. And maybe there's some worry about kind of the edge identifications now, but matrices kind of preserve the notion of parallelism. So all the identifications that made sense previously are going to continue to make sense. Okay, so now we have a space given by the space of all double slit tori, which I'm calling E, and I have dynamics on there given by SL2R. And I want to look at the particular one parameter family given by the Horocycle flow. So I want to look at the lower unipotent matrices as indicated by here. And I just kind of want to observe briefly that this is a vertical shear on the plane. Right, and the reason why I'm interested in it is because of its behavior on slopes. And so let's kind of flesh that out a little bit. All right, suppose I had a vector, xy, and I acted on it by the Horocycle flow. What this is going to do is it's going to produce the following new vector, where the only change that's going to happen is going to be in the vertical component. So now what I can do is I can look at the slope of the vector after applying Horocycle flow and ask, how does this compare to the slope of the original vector? Well, it compares to the slope of the original vector by just kind of decreasing the slope by the amount of time that I've flown by. Right, so if I have flowed by time u, then I just shrink the slope by time u. Okay, and in particular, we have the following observation: slope differences are preserved. Right, and this slope gap distribution is literally looking at slope differences, and so this indicates that the Horocycle flow is a really good one-parameter family of matrices to kind of consider in this context. All right, and so this is kind of indicating why Horocycle flow is important. And so now we can start to get into the dynamical question that I want to recast the slope gap distribution question as. So I want to consider the following transversal for double slit tori. So it's a set of, in words, it's a set of translation surfaces that have a holonomy vector that intersect this little region here, right? In words, it's a set of double slit tori that have a short horizontal saddle connection. So by short, I mean less than or equal to 1. Okay, that's what I mean by short. And so as an example of it, we can take the following picture here. This is a picture of, the holonomy vectors of a double slit torus. And what I'm saying is the following. If this is 1 and this is 0, and I have a holonomy vector that lands inside of this region, the way I do it with X, then omega is inside of this, is inside of W, the transversal. So now what do I mean by the phrase transversal? I mean the following. I mean kind of generically, schematically, we can draw the space of all double slit tori like this. And by transversal, I mean that it's some lower dimensional subset W with the following property. If I start off with an element inside of W, say omega, as soon as I apply the Horocycle flow, I leave. And so maybe this is clear by the discreteness of the holonomy vectors, right? If I have a short horizontal saddle connection and I kind of vertical shear this picture down, I'm immediately going to stop having a short horizontal saddle connection, and it'll take some time before I get another one by the discreteness of the holonomy vectors, basically. Okay, so this is kind of the generic picture that I'm looking at right here, given by the schematic. And now we're actually almost done with kind of recasting the question of slope gaps in terms of dynamics. And the key idea is the following: slope gaps are exactly return times to W. All right, so what do I mean by this? Pretend I had an element inside of W, right? Pretend I had an element that has short horizontal vector. When is HU of omega going to return to W? All right, so what does it mean for me to return to W? It means the following. It means I have some vector inside of my holonomy set, let's say the vector xy, such that when I horocycle flow by it, I get something that's short and horizontal. Well, here is exactly what I get when I horocycle flow by it. And this is going to tell me the conditions I need. The conditions I need are that it's short, which means that x better be inside of 0 and 1, and it's horizontal, right? So what does it mean for y minus u? So what does it mean for this vector to be horizontal? It means that the vertical is 0. Right? And so the vertical is 0 exactly when u is equal to a slope, right? So this is a slope. And maybe if I call this 1 and I call this 0, this is saying that the amount of time that I need to flow is just the smallest positive slope inside of the holonomy vectors. Maybe I'll call it S1, right? So the amount of time that I need to flow is exactly S1, because after flowing for S1, I'll land back inside of my transversal. So that's how we get it for the first return time, right? I'm saying that return time, I'm saying that slope gaps need to be return times, but here I'm only getting slopes. So how do we get slope gaps, right? So the way we get slope gaps is by the following. The first return time is a slope. What about the second return time? Well, the second return time is going to play a similar game. If I want to get something inside of the transversal, that means I need to land inside of this little sector right here. So I need something that lands inside of here. I know this guy right here is going to be the first time that I return. So the second time that I return is going to be the next biggest slope, S2, right? And so now what is S2 representing here in this picture? S2 is representing the total amount of time that I need to flow before I come back to the transversal. However, the total amount of time that I need to return, that I need to come back to the transversal is taking into account the first return time. So if I only want the second return time, I need to subtract the first return time. And now we're going to get a slope difference, right? So the second return time is exactly S2 minus S1, i.e. it's a slope difference, okay? And then we can play a similar game, and now we can try to formalize this idea. So let's go ahead and let R denote the return time to W, and let T denote the return map to W, right? So by return time, I just mean the amount of time that I need to wait before I come back to W. And T is a return map. So now it's like the induced dynamical system that says, all right, the new map, so if I have omega, then T of omega is just the amount of time that I need to wait before I come back. But if I wait that amount of time, then I've come back. So I'm in W. So this is what I mean by T, the return map. Maybe schematically, we have the following picture here. I have the space of all double slit tori. I have somehow lower dimensional subset of it, W over here. And I start off with an element omega. And so I flow omega by the Horocycle flow. And I flow, maybe it travels around, comes back. And whatever it comes back to, that's what I declare T of W to be. And then R of W is somehow the length of this chord that I've traveled, right? And so this is kind of formalizing some of the things that we've already been seeing in the previous slides. All right, and so now we're almost done, right? The key idea is slope gaps are exactly return times. And now that we have some notation set up, I can rewrite this as the following kind of equation. Slope gaps are exactly the return times to the transversal, right? When I is equal to 0, I'm going to get, S sub 1 minus S sub 0, which is 0, is equal to just the return time of omega. which is what we saw earlier. And as I let I be 1, 2, and 3, then I need to apply t to keep track of the next return times, right? T is telling me when I come back to the transversal, and then I can compute the return time from there. Okay? And so now we're almost done. So now I'm almost able to rephrase the slope gap question as a dynamical question. All right, so let's recall the slope gap distribution, right? It's basically the set of gaps that land inside of my favorite interval out of how many of them could have landed in there. Spiritually, kind of the thing that I kind of have here on the board right now is something that's very spiritually similar to the gap distribution question from the previous slide. There's like some small changes, but for the most part, this is the exact same gap question that we were looking at previously. Okay, and now using the key idea that slope gaps are return times, I'm able to rewrite it as the following sum, right? And so this sum looks perhaps a little crazy, right? I have kind of this indicator function on this pre-image and this induced dynamical system, and it's not clear exactly how it's helped, but at least it's saying the same thing, right? R inverse of I is literally tracking return times to I by the key idea return times are exactly slope gaps. And the fact that it's an indicator function means that this is only going to ring when I capture a return time. So it's exactly counting those slope gaps. And now the big kind of deal here is this right here is a Birkhoff sum, which means now we're able to use techniques from ergodic theory to try to understand it. And in particular, if omega is kind of a mu generic point in the transversal, then this is going to converge to just the integral of this function, right? And this is a characteristic function, so it's just going to converge to the area of this pre-image, which I've kind of written down here. And I hope this kind of indicates to you how you go from a slope gap distribution question to a dynamical question on the transversal, right? On the left here is kind of the slope gaps, and on the right here is kind of dynamics. And this is kind of the philosophy, the instance of the philosophy that I wanted to kind of share with you guys. I start off with this concrete question of slope gaps, and I turn it to a dynamical question on the space of all double slit tori. Well, maybe not all double slit tori, but I look at a transversal under Horocycle flow to double slit tori. And this tells me kind of the next steps, right? So the next steps are I need to understand W. I need to kind of parameterize it and give it some coordinates because that's what's in this formula. And what else is in this formula is the return map. So now that after I parameterize W, I should try to compute the return map in these coordinates, and then I can compute this area explicitly. And that's how you can kind of solve a slope gap distribution question. Okay? So thank you very much. Again, special thanks to my advisor for kind of teaching me a lot of these ideas, and to the Nearly Carbon Neutral Geometry Topology Conference. Bye.